You know, this conference was actually a little bit of an experiment for us. When we decided to put this together last year, we kind of challenged ourselves. Who are the coolest people that we could get to come? And would anybody even care to listen? I'm happy to say that we've gotten the likes of Google, Netflix, and ThoughtWorks, like our next speaker, to come here. And I recognize a lot of faces here, and I know that you guys drove through an hour and a half of traffic to be here, so somebody cares to listen, so thank you for that.
Right. So yeah, our next guest, Neal Ford, is from ThoughtWorks. He has a variety of titles, architect, director, but I think the one that's most important is he's an official meme wrangler at ThoughtWorks. He's going to describe to us what exactly that means and how that fits into your technology roadmap.
All right,
cool.
Thanks very much.
Thanks, Neal.
Good morning, everyone. So he asked me to describe my title. ThoughtWorks is one of those companies that they allow you to create your own title. And so my first set of business cards said application architect on them, which was a good reflection of the job that I was doing at the time. But then I realized in a lot of organizations, application architect means post-useful, meaning you spend more time in Visio or OmniGraffle than you do actually writing code. And so my title gradually morphed over time into the much more abstract meme wrangler, which is of course based on the Dawkins definition of the word meme, which is a viral unit of thought, so you're all familiar with the idea of internet memes. And wrangle has two useful definitions, to herd or to handle disputes and arguments. And so I chose that title a little bit tongue-in-cheek, but it has become sort of a self-fulfilling prophecy, and in fact, the book that I'm going to talk about today is really a result of that, because one of the things that I'm trying to do, one of the advantages of being a consultant, is you get to see a wide swath of projects, you get to see a lot of engineering practices, and you get to see things that work and things that don't work. You get a broader perspective on things, and I'm trying to harvest some of those perspective things in a talk like this. So today I'm going to talk about building evolutionary architectures, and this in many ways is the end result of all the things that Burr was just talking about. When you get good at continuous delivery and all these agile engineering practices, which are good things to chase all by themselves, but they're also really useful things because they enable a bunch of really cool capabilities like evolutionary architectures. This is a book that's written by me and two of my colleagues, Rebecca Parsons and Pat Qua. Rebecca is our CTO, and she has a background in evolutionary computing, which you'll see where that comes in just a second. Pat is one of our tech leads in London and has written a couple of small books on working with teams and team leads. But all three of us have been talking over the last few years about different aspects of how do you build evolutionary architectures. And we've consolidated that all together into a book, and it's a technical review right now, so it should be out within about a month or so, because it is essentially done. So what I want to address today is what are we talking about when we talk about an evolutionary software architecture? And of course, that brings up the question of what do we talk about when we talk about software architecture? One of the other things that I do is I'm sort of the subject matter expert advisor for the publisher O'Reilly on all things software architecture for their books and videos and their developer conference. And one of the things they asked me when I moved into that role was they wanted a really nice, succinct, clear definition of what is software architecture. And I said, no, because there's no way you can come up with a nice, clear definition. This is the closest I came, which is this mind map that starts talking about some of the aspects of software architecture, but there's still a bunch more there. But today I want to narrow in just on the structural aspects of software architecture. And in fact, talk about a couple of different ways about evolving applications and not just architecture. Because when we talk about software architecture, we think about the structural aspects of architecture. And those are the architectural patterns like microservices, and how libraries and frameworks go together, and how you construct applications. But there are a bunch of other things you have to think about to evolve real software systems as well, like data and security and performance and scalability and all those other concerns. So we'll put those aside for just a second, and let's just talk about the structural part of architecture, and then I'll talk about how to incorporate those other things like data into this equation in just a second. That's my water, right? So when you look at a software solution for some problem, you have some requirements. This is the reason that you're building this piece of software. So there's some problem that you're trying to solve. But part of the art of architecture is also determining a bunch of other important things that have to go into this. Things like scalability or resiliency or security, which is always a big concern. These are all those things that you have to think about when you build an architecture and have to balance those trade-offs between, for example, performance versus scalability, which sometimes have very different characteristics. And so that's part of what you do as an architect. In fact, I was working with a client very recently, and they're in the process of taking their platform and rebuilding a bunch of stuff. And so they showed me a spreadsheet that had 66 rows on it of here are all the things, desirable characteristics we want in our new architecture. So it was 4 nines of availability and a certain level of resiliency, et cetera. So those are all the extra things above and beyond the requirements that they had described. But then the question becomes, if I define all those things like scalability and performance, et cetera, how can I make sure that those things stay true over time? And that's part of this idea of evolutionary architecture. Because I don't want those things to degrade over time as I keep adding to my system. So these are all these characteristics of architecture that we colloquially call the illities of software architecture. This is a partial list from Wikipedia, and you cannot build a software system that supports all of these. So you have to pick and choose some really important ones that you want to support for a given solution. But what we want to do is add a new illity to this list, which is evolvability, the ability to evolve your architecture and make changes to it. But in many ways, this is a different kind of characteristic than all these others because it's a meta characteristic. Because evolvability really means that if I have defined an architecture and I've identified performance as an important characteristic, I don't want performance to degrade as I keep adding new behavior to my architecture. And so evolvability in many ways is a meta characteristic that wraps all the other characteristics and preserves them over time. And that brings up the question, once I've built an architecture, how can you prevent it from gradually degrading over time? So when that list of enterprise architects showed me the spreadsheet with 66 things on it, I said, hey, it's great that you've identified those things. When I come back in 6 months, how are you going to validate that any of those things are still true? It's like, well, each one of those things would be an ad hoc test of some kind. There's got to be a better way to manage that. But there's another fundamental problem as well. And that has to do with long-term planning in the software development world. Enterprise architects in particular love to create things like 5-year plans. But that's a problem in the software world because we live in a dynamic equilibrium. So if you think about the software development ecosystem, and that includes all the tools and the frameworks and the best practices and all the things that we know about building software up until about 10 minutes ago, that is the software development ecosystem. And that's where we live and breathe, and that's where we build stuff. But this is an equilibrium, but it's also extremely dynamic, and it may change at any time without letting you know. And a great example of this is when Docker hit our ecosystem a few years ago. Now, if 2 years ago you made a 5-year plan as an architect and didn't include Docker, as soon as Docker hits our ecosystem is fundamentally changed forever, and you can take that 5-year plan and wad it up and throw it away because it's now become irrelevant. Long-term planning is hard when the thing you are planning against can fundamentally change at any time. And so we think predictability is shot in software. But if you can't predict, the next best thing is to be able to accommodate change gracefully as it occurs. And that's this idea of building an evolutionary architecture. For a long time, one of the colloquial definitions of software architecture was the stuff that's hard to change later. There's a famous quote by Ralph Johnson. Martin Fowler said that architecture are things that people perceive as hard to change. But then, some architectural styles came along like microservices that expect change. So change is built into the architecture, so you can no longer say that that's the architectural elements because it turns out if you pay attention to it, you can make changes in architecture. So here's our definition of an evolutionary architecture. An evolutionary architecture supports incremental guided change as a first principle across multiple dimensions. And let me talk about the dimensions part of this first, and let me narrow in for just a second on just the technical architecture part of your solution. And this is going to be whatever architectural patterns you're using, whether monoliths or microservices or microkernels or whatever. This is also the tools and frameworks and all the things that you support as building your architecture. And this is the thing you think about when you think about software architectures, all these structural elements. So let's talk about the inherent evolvability of different kinds of technical architectures. And we'll start with the degenerate case, which is the big ball of mud architecture. This is a technical diagram, a visualization that I captured from a client project that I worked on, where all the little sub-pixel sized dots are classes, and the red lines are connections between the classes, and the bolder the lines, the more connections there are between those classes. So imagine, if you will, and some of you may not have to imagine too hard, making a change in an architecture like this. So let's say I need to change data access, how that works in this architecture. Well, you make a change in one place, and that's going to ripple out to 15 other places, and of course changing those places is going to ripple out. And so this is a miserable kind of experience. And so from an evolutionary standpoint, we basically have 0 dimensions of evolvability here. It's really hard to make changes in this architecture, which is why we don't build many of these, at least not on purpose. We're much more likely to build things like layered architectures, which separates all these responsibilities in distinctive layers, and now it's relatively easy to go in and make a technical change like swapping out the persistence layer, and so this has a dimension of evolvability. We can now evolve part of our system without breaking all the other parts. Now there's just one dimension here, which is the layers in the technical architecture. Even though there are 4 layers, we have 4 opportunities to do this evolution, but it's still along this one technical architecture dimension. Microkernel architecture, which is popular in things like IDEs and browsers, also has a dimension of evolvability because you can add new plugins and enhance the behavior of the architecture that way. Things like REST, so these don't have to be purely structural things. REST, in particular when you get to the hypermedia version of REST, part of the idea is that when you make a request for a resource, what comes back to you is data, but also what comes back are the links to the next steps in the workflow, and so your client just follows that link to get to the next link, and so the provider can change those links and change the workflow without notifying the client, so that's a dimension of evolvability. But let's talk about, I'll talk about this domain perspective in just a second. Let's talk about microservices, which is all the cool kid architecture right now. One of the underlying philosophical drivers of the microservice style of architecture is this idea of a bounded context. Each one of these services is completely decoupled from all these other services and lives in its own bounded context. And so from an evolvability standpoint, microservices have n dimensions of evolvability, where n is the number of services that you have. Because if I want to change the database from Mongo to Postgres for this service, none of the other services care about this because none of the others are allowed to couple directly to that piece of infrastructure. And so this is an example of an evolutionary architecture. And this is what we mean by across multiple dimensions of architecture. Because I would argue that all software architecture is defined to allow you to evolve in at least one dimension. So that's why we build layers or microkernels. What we're interested in are families that allow you to evolve in multiple ways at once. And this is not just for exotic new kinds of architectures like microservices because of composability. Architectural patterns very often compose quite cleanly inside one another. So for example, let's say that you have a business rules engine that's implemented as a microkernel, and that is the implementation detail in the business layer of a layered architecture, which is in turn the implementation detail in a service in a microservice architecture. You have several layers and ways to evolve that because of the way you've composed those architectural patterns. So that's what we mean by multiple dimensions in terms of technical architecture. Let's talk now about incremental change. And there are 2 aspects of incremental change I want to talk about here. One is the operations and DevOps side, and one is on the developer side. So let's assume for a moment that you live in a world that Burr was describing, where you have a good service-based or microservice architecture with good isolation between services. You have good 21st century DevOps and things like deployment pipelines in place. Let's talk about an evolutionary architecture. And so it's quite common in this world that component deployment and feature release are decoupled from one another. In fact, a lot of companies that do continuous deployment, they're not barraging their users with brand new features all the time. They're continuously deploying services, and the features inside them are still turned off. So either underneath feature toggles or by selective routing in a microservice environment, you can put a new microservice live and just not route any business to it yet, but that allows you to vet the operational characteristics to make sure it plays nice and it monitors and logs, et cetera. And so in this world, you deploy components, and then at some later date, you release features by either routing to them or turning on feature toggles. And it's quite common in this world that applications consist of routes between particular services. So let's say that you run a catalog site. We have a fake company in our book called Penultimate Widgets, the second best widget manufacturer that's trying to become number one. And they have a catalog site that has widgets that they sell, and you can star rate widgets by how much you like them. So they have a star rating service running in their ecosystem. And then one day they release a better star rating service and put it live alongside the existing one. They don't force anyone to use it, but they now make it available in their architecture. And now over time, services that need star ratings will gradually migrate over to half-star ratings until eventually no one is pointing to the old star rating service anymore. One of the magic tricks that Netflix taught us about architectures like this is that you monitor not only services, but also the routes between services. And if you find a service that no one has routed to in a given amount of time, you disintegrate that service out of your ecosystem. That's an evolutionary architecture, the ability to put new behaviors alongside existing ones, allow people to selectively migrate to those things, and then get rid of the old stuff that you don't need anymore. So that's the incremental part of this equation. But now let's talk about the guided part. And now I need to pull in all those extra ilities, because we talked about the technical architecture evolution, but you can't evolve your technical architecture and leave your relational database back in the tar pit where it's still living and breathing. And you can't evolve your technical architecture and start opening up security holes. That would be bad with a capital B. So there are all these other perspectives we need to take on architecture as well, like the data architecture and how things are organized, how we evolve our schemas. I'll bring up this book, and it's hard to read, but I'll bring up a bigger copy of it in just a second. This is a highly recommended book, Refactoring Databases by Scott Amler and Pramod Sattelage, that was written 10 years ago. So it just had its 10-year anniversary. And I recently bumped into Pramod, and I told him he needs to re-release this book and just flip the subtitle and the title. And I know you can't read it up here. The subtitle of this book is Evolutionary Database Design. And the title is Refactoring Databases. So would you not buy a book right now called Evolutionary Database Design? Because everybody needs this right now because of this move into service-based and microservice architectures. You have to be able to restructure your data as well. So this is just a classic example of a book that was about a decade ahead of its time, still incredibly relevant. And I'll talk a little bit about how you deal with the data side of this as well. But that's only one thing that you have to think about in addition. You have to think about security. And so there are all these other perspectives that you have to pick up on architecture, and that's where the guided part of this definition comes in, and this idea of a fitness function. Excuse me. So this is where Rebecca's background in evolutionary computing comes in, because when you're doing evolutionary computing, when you're building a genetic algorithm, you're trying to build an algorithm that gets better at each subsequent generation all by itself, so it's evolving its behavior. Someone has to determine what better means for this algorithm, and that's what a fitness function is. A fitness function is the thing that you evaluate against your algorithm to see has it gotten better or not as it's been evolving by itself over time. And so we're co-opting this idea of a fitness function from evolutionary computing and applying this to software architecture. So what we're going to do is take this fitness function concept and take all those important architectural characteristics we want to protect, like scalability and security, et cetera, and build fitness functions around those in the form of metrics and tests and other sorts of verification mechanisms to make sure that as we make changes to our architecture, we continuously vet and make sure that we haven't broken the things that we've identified were the important preservable aspects of that architecture. And I'll give you a bunch of examples of these guys in just a second. And so that's our definition. An evolutionary architecture supports incremental guided change as a first principle across multiple dimensions. And that now gives me enough to get to the agenda for this talk. The first part of which is a lengthy definition of evolutionary architecture, which you just lived through. And now I'm going to talk about a couple of more aspects of each of these three things: incremental change fitness functions, and what we call appropriate coupling, and some superpowers that you get from this. So let's go back to this idea of fitness functions for a second and give you some examples of what we're talking about here. So like I mentioned, these may be things like metrics or tests. So we're co-opting a bunch of things that already exist out in the world, but what we're trying to do is put a bunch of disparate things into a singular category, which is we can evaluate this characteristic and determine whether it's good or not, or true or false. And so this encompasses metrics and tests and lots of other stuff. And we've also defined some categories that these guys live in. So atomic fitness functions are ones that run against a single context. A unit test is a good example of a atomic fitness function, whereas a holistic one needs to run in a shared context. A batch means that it's run on demand or through something like continuous integration, versus continuous, which means it just runs as an ongoing continuous thing. So let me give you examples of each of these. And I'll talk about atomic and batch first. So let's say that you're an architect on a monolithic application. One of the things that you want to prevent inside a monolithic application is what's called a component cycle, which is where you have one component that talks to another component that talks to another one that talks back to the original one. You have dependency between these guys, and this is undesirable because now I can't take a single one of those components anywhere. I have to bring the whole nest of them. And this is even worse if these are nested up with a bunch of others, and now you got this kind of sticky mess. And so as an architect, what I'd like to do is prevent those cycles from happening. Now, one of the ways you can do that is to institute a policy and say, okay, at noon on Friday, there will be public meetings for any developer who adds a cycle into the code base over the past week. But even that doesn't work because you got too many other things to think about. This is what we use an atomic fitness function for. So JDepend is a library in the Java world that can look at and analyze to see if you have cycles in your code base. And so you can go through the effort of chasing all the cycles out of your code base and then put this unit test in place. And now as soon as the developer inadvertently creates one of these cycles, you get a failed unit test. You don't get headaches at the architectural level in 6 months or a year. You can also do some things like directionality of imports. So you can define rules here to say what direction imports happen. So if I say that web depends upon util, if I try to come in and import web into util, it won't allow me to do that. It'll fail that test. So as the architect, you can define some rules about how things fit together. These are all atomic fitness functions because they run against a single context, which is the application, and these are modeled as unit tests. Batch holistic fitness functions are combined multiple systems, and there are two different variations of this. So one of these is, let's say that I have a scalability test that runs against my application, and one of the ways that I get good scalability is turn on caching. I also have a security test that runs against my application to make sure that I don't have any security holes, and one of the things it checks for is stale data. And when I run those individually, everything is okay, but when I run them together, the caching makes the data live so long that now I've violated, my security fitness function. And so this is an example of a holistic fitness function because both these things need to be run at the same time because I'm trying to vet some combined characteristic, an interaction between two of my architectural characteristics. So that's one version of a holistic fitness function. Here's another example. And this is a really common practice in the microservices world of how do you make sure that integration points don't break. So you have all these really autonomous teams building things, building new capabilities, but they also have to integrate with one another. How do you make sure that all this innovation doesn't break those integration points? The common practice here is this idea of consumer-driven contracts. So the team on the left is a service provider, and they're providing some bits of information to all three teams on the right. The idea of a consumer-driven contract is that all three of the teams on the right put together a set of tests and then hand them to the team on the left, and the team on the left promises, I will keep these tests green always. And so they're taking on the responsibility of managing that contract for those teams. If that changes, if the service changes and doesn't break any of the contracts, then it changed in a way that nobody cares about. If a change does break one of these contracts, then that's a placeholder for conversation to get back together and reestablish that contract. Now, I'll just say parenthetically here that this goes back to what I was saying before, that this is really the next generation or the maturity beyond what Burr was talking about here, because notice that in this world, if you run around with broken builds for 2 or 3 days at a time, it's not going to be a happy place, because we rely on the continuous builds being green to manage things like integration points, to make sure that integration points work. So broken builds in this world mean that lots of different things may be broken, and so you have to be really diligent and have a lot of engineering discipline to make that work correctly. Atomic and continuous fitness functions are things like, in the DevOps realm, are things like monitoring and logging. So a really common practice in microservices is to create correlation IDs. You tag that onto a request so you can follow that ID across all the services that it touches for debugging purposes. So monitoring and logging are super popular in that world, and these are continuous kinds of activities. So one of the things that you may want to do is time how long transactions take in your production system as a metric to see how things, the health of your overall system. That would be a continuous atomic kind of fitness function. And then the most elaborate and complicated kinds, but maybe most valuable, are these continuous holistic fitness functions. And the perfect example of that already exists out in the world is something that Burr mentioned, which is Netflix's Chaos Monkey. And Chaos Monkey is an interesting case because when Netflix decided to move all their stuff to Amazon, they realized that they don't own their operations anymore, and they worried about resiliency. How can we guarantee resiliency if we don't own that capability? And so that encouraged them to create the Chaos Monkey, which makes Amazon instances misbehave in all sorts of interesting, chaotic ways. And have since open sourced the entire simian army of these tools that go and attack different aspects of your architecture. You remember about, was this 3 or 4 months ago, Amazon East was down? And it's always entertaining when Amazon East is down of how many things break. So I have a Ring doorbell, and it turns out when Amazon East is down, you no longer get the little videos on your Ring doorbell, because apparently they're using Amazon for that. But while Amazon East was down, Netflix stayed up because of the Chaos Gorilla. They simulated an entire Amazon data center going down with the Chaos Gorilla, and they wrote code to make sure that it didn't affect them, and it didn't. And this is interesting for us because notice that this is a continuous thing. They don't run the Chaos Monkey at 3 o'clock on Tuesday afternoon. The Chaos Monkey lives in their architecture, which means that their developers, when they write services, know they have to enforce a certain level of resiliency, because if they don't, as soon as they put it live, the monkey's just going to kill it. And so this forces their developers to work at a higher level because there's this continuous function running to make sure that you've dotted all your I's and crossed all your T's to make sure that everything works correctly. And this is testing the resilience of the entire system. So this is testing, I guess, resiliency, because you can turn any word into an ility word. And there are several other examples of these. We have temporal fitness functions and several other categories. We also have this concept of a system-wide fitness function, which is the composition of all your individual fitness functions. This is not something that you would ever actually execute, but this is really important because what the other mind shift we're trying to put on architects is to start treating architectural characteristics as evaluable things. So the 66-line spreadsheet that those architects gave me, and I said, how in 6 months are we going to validate that these things are still true? The answer to that question is we're going to build a fitness function for every single one of these characteristics. You've identified that these things are important, so let's build fitness functions and wire them into your architecture so that now every time you make a change to your architecture, you know that that characteristic is still true. So here's an example of some fitness functions that we ran on a project. We graded ourselves, 0 meaning perfectly good, and 5 meaning we need some more work on it. And these are the common kinds of things that you see in architectures like configurability and security and availability, including some things like legal requirements. Now, although effort is still ongoing, we have not managed to automate away lawyers yet. And I don't know if we're going to have any success doing that. And so some of these may be manual stages. So all of this doesn't presuppose automation. It's perfectly legitimate if you have some sort of a regulation that you have to adhere to, some sort of legal guidelines. You can build those into your deployment pipeline, but I want these things considered as objective results. These are true-false tests that a person is applying, but I still want all these characteristics to be treated as the same kind of something that we can evaluate to determine if things are correct or not. So let's talk a little bit more about incremental change at the developer side of the world. And there are a bunch of prerequisites here, and it's not surprising that some of the same books show up from Burr's deck as mine. Continuous delivery, there's the refactoring databases book again. There's Release It from Mike Nygaard, and one of my colleagues, Infrastructure as Code, just came out. So these are all prerequisites for these agile engineering practices, including this idea of a deployment pipeline. So Burr mentioned this in his talk. This is a common feature in a lot of agile projects, and this is how we guarantee that all of our fitness functions are going to be applied on a regular basis, because what we're going to do is wire our fitness functions into our deployment pipeline. So now every single time a developer makes a change, when continuous integration picks that up, they're going to run our architectural fitness functions to make sure that we haven't broken those things. And so a deployment pipeline makes it easy to make sure that all those things are still true. And in fact, the client we were talking to who wanted to give their platform to a bunch of their customers and allow them to further customize their platform. But now they're worried that if we put a lot of work and effort into build this really nice scalable platform, but then we give it to our customers and let them start extending it, how are we going to make sure that they don't start degrading the scalability and other important things, or even more critically, things like security? And so what they're going to do is when they give them that source code, they're going to give them the deployment pipeline as well. So they're not just giving them the project, they're giving them the build of the project so that they can keep applying those fitness functions and then hopefully add a few more of their own after the fact. And so really the deployment pipeline here is the engine that runs this idea of evolutionary architecture. This is where you apply things like fitness functions, and really the velocity in which you can make changes determines how fast you can evolve your architecture and how fast you can make changes in your architecture. So let's talk a little bit about the last of these, which is appropriate coupling. And a little bit about the database. It's all fine and good as architects to talk about, restructure your monolith into microservices, but you'd better call your DBAs and let them know you got this in mind as well, because it's going to have a big impact on them as well. One of the things that continuous delivery taught us is that you can't just look at source code. Software applications consist of lots of moving parts, and you have to consider all those things. And many of you find yourself in this situation, where you have 3 different applications that are using a database as an integration point. And this is so common because it's so easy. I need these 3 applications to share some stuff, and they're all talking to the same monolithic relational database, so we'll just let them share all that information. And then a few years later, you realize, oh no, now I've coupled all these things together forever, and now I want to evolve the behavior of application A, and that is going to entail a database schema change. But now I can't change B and C because they still need to do what they're going to do, so how can I get out of this sticky problem? The Refactoring Databases book has a solution to this called the expand and contract pattern. So let's say that this is our initial setup, where I have balance on customer, and on behalf of application A, I need for balance to be on account instead, but B and C still need it to be on customer. And so it's quite common in these refactorings to have a transition phase where now I'm going to add balance over on account and then create a trigger to synchronize those two. I basically now support both versions of the API. And now I can evolve applications A behavior and not break the other two at the same time. This is a pattern in the Refactoring Databases book called the expand and contract pattern for doing a database refactoring. And this allows you to do that same kind of shift and move into the future at your database as you can do at the architectural level. Another common side effect of these kind of architectures is highly decentralized governance. Because when you have really highly isolated architectures like microservices, maybe this team decides they want to use Mongo, and then 6 months later realize that Mongo is a terrible choice, and so they want to replace that with Postgres. Nobody else cares because no one is allowed to couple to infrastructure pieces within these services. And in fact, one of the trickiest things about doing monolithic governance, particularly around tool and framework choices, is that you have to choose something that works for everybody. So let me put on my enterprise architect shoes for a second, and now I want to pick the relational database that the entire company is going to use. Well, I have to go to each team and find out which team has the gnarliest, awfulest database problem to solve, and the database I choose has to be able to solve that nasty problem. And then I have to go to the integration architects and find out the nastiest, awful problem they have, and I have to find a message queue that can handle that nasty problem. The problem, though, is that because everybody's sharing everything, I'm imposing the maximum data complexity on every single team. Even though only 10% of my projects need the industrial strength database, now everybody's forced to use it because everybody's forced to share the same thing. This is the motivation in the microservices world of each project can get their own technology stack when it makes sense to do so. They're not trying to let 1,000 flowers bloom. What we're trying to do here is say, let's right-size the technology choice for the size problem we're trying to solve and not try to impose the same massive complexity on everybody. Now, in most large organizations, you can't afford to let every single team go artisanal and build their entire unique stack. And so what we see out in the world quite commonly is what we're calling Goldilocks governance. We have a small stack, a medium stack, and a complex stack. And when new problems come in, you assign one of those stacks and use that to solve the problem. So how do you take advantage of all this stuff? Well, just like choosing architectural characteristics, the first thing you're going to do is to choose what dimensions you want to protect in your architecture. So these are going to be important characteristics that you've chosen in your architecture. And then what you're going to do is build fitness functions for each one of those characteristics. That will protect those characteristics going forward in time to make sure that they don't break. So you identify those fitness functions and wire them into your architecture. And these may be atomic or holistic. These may be manual or automated. There are a variety of different flavors that these can take on. Then you apply incremental change by using something like a deployment pipeline to allow you to apply those fitness functions every time you make a change to your architecture. Deployment pipelines also allow you to do things like continuous deployment and a bunch of other advanced DevOps tricks. And this will let you create a really good tight cycle time for your project. And while a lot of this stuff happens up front, you can also keep an eye out for things that are changing as you build things so that you can accommodate breaking changes that happen along the way. So you identify these things up front, but you also take advantage of them as time goes by and build new ones as you identify something weird might be happening in your architecture. So the last thing I want to talk about here is some of the advanced business capabilities that I alluded to earlier and a case study of how you can utilize an evolutionary architecture. This is from the GitHub blog. This is an installment called Move Fast and Fix Things. So GitHub is a very agile company. They do 60 deploys a day on average, so they do continuous deployment as part of their ongoing architecture. And at some point, they encountered a problem. So it turns out since day one at GitHub, the way they've done merge is to just shell out to a command line, have Git do the merge, and then suck it back into GitHub, which works perfectly because Git knows how to merge projects. The problem is that doesn't scale particularly well, and GitHub has to operate at scale, and so they reached a point where we need to replace merge with our own handwritten C library version of merge. And this is where the terror comes in. Because now I need to replace a core important part of the GitHub website, but you can't break merge. It's worked since day one on GitHub. You can't introduce regressions on something as critical as merge. And so the way that they manage that was by creating and open sourcing this thing called Scientist. And here's what Scientist does. So Scientist has a use block and a try block. The use block is the old code, and the try block is the new code you're trying out. And so what Scientist does is it decides whether or not to run the try block. So for the merge experiment, they did it for 10% of users, got the try block. It randomizes the order in which these run, measures the durations of all these because we're measuring performance as well, compares the result of try to use. Only when you hit try does it execute the try block, but it always executes use and always returns the value of use. And so the worst case for people who are in the experiment is you get exactly the same result as you would have always have gotten, but we ran this other version of the algorithm as well so we can compare them, swallows any exceptions, and then publishes everything. And so when this went live, you can see the number of merges that they were doing is in the 2,000 numbers, and there are a few mismatches down here. So if I zoom in on the bottom, you can see there are a few mismatches that are starting to pop up that they have to resolve as bugs. But the performance looks really good. So here's the green line. This is the new code, and that's the old code. But the fascinating thing to me were the bugs that they found and how they resolved them. They found out that the shell script was doing a faster conflict resolution because it was bailing as soon as it found the first merge, and their library was going all the way through, and so they fixed theirs to bail right away. They were writing an index to disk that they realized they didn't need to do anymore, which is causing a performance bottleneck, so they fixed that. This is an interesting one. If the ancestor had a file with one file mode and one side of the merge had removed the file and the other side had changed the file mode, it would report merge successful. This is a bug in Get, so they submitted a bug report to Get. This is the one that will keep you up at night. It turns out that if you give GitHub two projects that have exactly 768 merge conflicts, GitHub will come back and say, everything's cool. It'll have all the merge markers in the file, but it'll still say, everything's great. How is this possible? And why this magic number? Well, as a clue, 768 is 256 times 3. So what was happening was that shell script has a return value, and if you get a certain number of merge conflicts, it would roll over the return value, the integer, back to 0, which means successful. And so they found a regression bug in their original code that existed since day one and fixed that, and they found a legitimate bug. They did 4 days of iterating on this process, doing 60 deploys a day on average, and they managed to get the experiment to run 100% of the time with no mismatches or slow cases, and so removed the old code and left the new code in place. That's an example of an evolutionary architecture, the ability to make substantive changes to your architecture without breaking a bunch of stuff, and maybe even fixing a few little bugs that are floating around in the process. So our goal here is to build architectures that encourage evolvability. We want to start thinking about architectural characteristics as evaluable things. These are things that can be tested. Some of these tests are hard to put together, but once you put them together, they're incredibly valuable. 5 years ago, people said, you could never write source code that would produce a computer, but people kept chipping away at that problem, and now we have tools like Puppet and Chef and Ansible. And now, we also want to define and protect all these important architectural characteristics and eventually utilize this to build new kinds of business value and enable hypothesis and data-driven development and some capabilities that we don't have now in many cases. We have a website, evolutionaryarchitectures.com, and we're going to put book samples and other stuff there, and the book should be out around July or so. Thanks very much for having me. I hope you enjoyed it. Thanks.
So far, thanks, of course, to our awesome presenters. Just wanted to give everybody a heads up. This is being streamed live on Facebook. So everything that we're seeing is on Facebook Live. We're also going to take those videos, encapsulate them, put them on YouTube so that you guys will have access to those afterwards.